Thank you. Oh, I should put this on now. Just a second. Can you all hear me okay? Yeah, not that big of a room. Hi, thanks for having me. Thanks to the organizers for the invitation. Today I'm going to talk about some work that's joint with Scott Larson at UGA. And also, I've changed the title of my talk from what it was in the abstract, so it's the same content, just a slightly different title. But I should definitely start this talk with two warnings. The first is that I have very recently become a mother, so I am not thinking at my most fresh at the moment. So if I have long pauses when you ask me questions, this is why. And the second warning is that I've been working on this project for a few years now. So I think a lot of members of the audience have heard some incarnation of this talk in some form over the years. So sorry if you're in that portion of the audience, but I did it. There's a few more examples included in this version at the end. So if the beginning stuff is really familiar to you, hang in there, and maybe the examples at the end will be interesting. Okay, so I'll start with an overview. So here's a plot synopsis of what I'm talking about. The beginning are these pieces of data. So if we start with a connected reductive algebraic group, a holomorphic involution of it, and some finite index subgroup of the fixed points under that involution, from these three pieces of data, we can construct two things via two very classical constructions. So the first is associated to these three things, there's some real reductive group. And then also associated to these three things is a certain module over the Hecke algebra. And this thing I'll call the Lusztig-Vogan module. And I'll remind you more about this construction later. If maybe you've never seen it before, I'll tell you about the construction. But the point is that this is the only input data, and by classical constructions, we get these two things. And they're related in the following way. The admissible representation theory of the real Lie group corresponds to the structure theory of this module. And more specifically, if we want to know irreducible character formulas for admissible representation, these can be read off of certain polynomials that appear as a change of basis matrix in this module. And so what I want to do today is I want to tell you about two categorifications of this picture, because this is the conference on categorification, and so that's what I should be talking about. So my first goal for today is to describe a geometric categorification and also an algebraic one. The geometric one I'll only touch on briefly, and I'll focus on the algebraic categorification, which is in terms of circle bimodules. And then what I want to end with is I want to show you a few examples. So I want to draw pictures of these categories that we get, so we can get a sense of what they look like if you're someone who's familiar with module categories over circle bimodules. So this is where we're going, but as always, we should start at the beginning. So here's the plan of what we'll cover. I'll start by spending a fair bit of time telling you what the Lusztig-Vogan module is, because maybe you haven't thought about real group representation theory too much. And then I'll briefly describe its geometric version, the first of our categorifications. And then I'll spend more time talking about the algebraic version, and finally I'll end with some examples. So we'll start here. Also, you should interrupt me at any time with questions. Like I said, I might answer them very slowly, but I'm happy to have them. So to start with, we'll fix this data that I mentioned at the beginning, some complex reductive group, holomorphic involution, subgroup of the fixed point set. And for the most of the talk, we'll keep the running example of SL2. So you can always keep this in the back of your head. So this is maybe my favorite real Lie group. It has a very nice structure. So in this example, we can see the real Lie group SL2R by taking the complex group SL2C and taking this involution, which conjugates by this matrix. And then the fixed point set is diagonal matrices, which look like a copy of C star. So keep this in your head if you'd like. And then a very classical problem in this world is to study or understand the real Lie group by studying its unitary representation theory. And this has been a problem that people have been thinking about for many years, maybe 70 years, maybe longer, a very classical problem. And the approach to this problem, which is on its head an analytic problem, it's a problem about studying unitary representations. Harishchandra realized that we could recast the whole problem algebraically by transferring to the land of GK modules. So starting with a unitary representation of a real group, we can differentiate and get a representation of the complex Lie algebra. And then we can also take the representation and restrict it to a maximal compact subgroup of our real Lie group. And this gives us a module over either a compact Lie group or its complexification. And both of these worlds are easier. So the representation theory of complex Lie algebras and the representation theory of compact Lie groups are pretty well understood. So by starting with this harder problem, representation of real Lie group, we can transfer it to two easier problems. And this is what Harishchandra realized. And the reason why it works, it's not at all clear that this should work at all, because both of these processes are losing information. When we take the representation of the Lie algebra, it doesn't tell us everything about the representation of the group. And same, when we restrict to a subgroup, we lose all the information about the entire group. But it turns out that these two pieces are exactly oriented so they capture everything. So by differentiating, we capture all the infinitesimal information about the real Lie group. But we lose anything that lets us distinguish a Lie group from its coverages. But if we keep track of the restriction to the maximal compact, we capture all the fundamental group information about our Lie group. So it exactly makes up for what the Lie algebra loses. So together, we can transfer our problem of unitary representations to studying two easier worlds. And there's one adjective that's already showed up in my talk that I should explain what it means. And this is this notion of admissibility. So it turns out that if we start with an irreducible unitary representation of our real group, we restrict to the maximal compact subgroup, then we know we can decompose it into a direct sum of irreducible representations, or as a representation of the compact group. But if we start with something infinite dimensional, it's possible that one of these things shows up infinitely many times. But if we start with a unitary representation, this doesn't happen. And so this property of having each irreducible k-type only show up finitely many times is what admissibility means. So if we start with a unitary representation, the point is that this leads us to a GK module, but not just any one, an admissible one. So that's what this adjective is around. And this is actually what today's talk is about. So it's sort of under the umbrella of representations of real Lie groups, but I'm going to quickly go do away with the real Lie groups and not talk about them again for the rest of the talk and work instead in this world of GK modules. Okay, so I've introduced for you a class of representations, which I think are interesting, admissible GK modules. And maybe the first thing we ask, if we have some class of representations we want to understand, is how to classify the irreducibles. And in this case, the irreducibles have a very nice geometric classification. If we have some Borel subgroup inside of our complex group, we can look at the action on the flag variety of this maximal compact subgroup. It acts with finitely many orbits, and information about those orbits gives us a classification of irreducible admissible GK modules. So for every orbit, we have a certain number of k equivariant local systems. For each one of these, we have exactly one irreducible admissible GK module of some fixed infinitesimal character. And so this is a really nice answer to the classification problem. And it's even nicer because it's quite explicit. So not only is it a parameterization, but we can actually construct these representations if we use Valence and Bernstein localization and think about D-modules. So this will be the only slide where D-modules show up. It's just nice to realize that they give us a method to build these representations. So over here on the left, I just have a little diagram. If we want to look at these irreducible GK modules, which are sometimes called Harishchandra modules, we can localize and look at corresponding D modules, k equivariant D module from the flag variety. And then once we're in D module land, there's a natural procedure for classifying our simple objects. We take some local system on an orbit, we can push it forward in one of two ways, using either a shriek or a star push forward for D modules. And then these have an irreducible quotient or irreducible submodule that's unique, and all irreducible k equivariant D modules are of this form. So we can take this nice D module construction and then take global sections of everything in sight, and these land us with certain irreducible admissible GK modules, and that's how we get them. So this world has a very explicit and nice classification of irreducibles. Okay, let's see this in an example just quickly, so it's nice so we can have our feet on the ground throughout. So what does this look like for SL2R? So for SL2R, our group K is just the group of diagonal matrices. And this acts on the flag variety, which in this case is a copy of CP1 with 3 orbits: North Pole, South Pole, and everything else. So we have 3 orbits, 2 closed orbits and 1 open orbit. And then on these 3 orbits, we have 4 k equivariant local systems. So on the closed orbits, we just have the trivial local system. And on the open orbit, it's important to notice that k equivariance really shows up in our classification, because this open orbit looks like a copy of C star. So we have Z many local systems, but if we ask about k equivariant local systems, it turns out that there are exactly 2. There's the trivial one and there's this Mobius band. And the way we can see this is we can parameterize k-equivariant local systems by looking at the stabilizer of a generic point in the orbit. So in this case, we can compute the stabilizer really explicitly. The action looks like this. The stabilizer is a copy of Z2, so we have two local systems here. Yeah, Ben.
I'm just confused about one point, which is that C star isn't compact.
I snuck a complexification in there. So yeah, so when we actually, when I think about GK modules, I'm looking at the complex group K. And it doesn't really mess us up so much. Good point. Any other questions? Okay. Okay, so I told you about some classic representations. I gave you what I think is a nice parameterization of simples. And so what's the next question we ask about a classic representations? We ask about their character theory. So in this case, we have some finite length abelian category, and it has a classification of simple objects, which is given as quotients of certain standard objects, which are easy to define. And so that means that in the Grothendieck group, we can take the class of the standard object, decompose it into simple objects, and ask what multiplicities show up. So classical representation theory question, what are these multiplicities? And the answer here is that they're given by the Lusztig-Vogan module. So this certain module for the Hecke algebra exactly answers this multiplicity question. And down here, I just wrote my Hecke algebra conventions. So if you see symbols show up later in the talk, delta S is my standard basis, BW is my Cauchy-Linguistic basis. Okay, so the upshot of what I've told you so far is that the Lusztig-Vogan module tells us something about the character theory of real groups. But I haven't actually told you what it is. So I'll do a brief overview of how we construct this module. And the idea behind its construction is to imitate Cauchy-Linguistic theory. Yeah.
Sorry, how does the module tell you the multiplicities? Is it like?
Oh, yeah, I'll get to this precisely in a second, but it's a change of basis matrix. And so the module, just like Cauchy-Linguistic theory, has two natural bases, and entries in a change of basis matrix give us some version of Cauchy-Linguistic polynomials and evaluate them at one. Yeah, great. Any other questions? Okay, so here's a brief overview of how this thing is actually built. So we're trying to kind of play the Cauchy-Linguistic theory game. So what's the first ingredient in Cauchy-Linguistic theory? Well, we have the file group. That's what parameterizes the irreducible representations we care about if we're thinking about category O. And so the thing that plays the role of the file group here is this set of orbits plus local systems, because this is the set that parameterizes our irreducible objects. And then our next ingredient in Cauchy-Linguistic theory is the length function, which we can realize as dimension of Bruhat cells. And so here we have some geometric world, and so we need a length function, and it's natural to take it to be dimension of an orbit. The next ingredient is the Hecke algebra itself in Cauchy-Linguistic theory, which at first glance we can just think about as a free module over this Laurent polynomial ring with a basis given by the file group. And so we can do the same thing here with our basis. So we're going to set MLV to just be a free module with a basis given by our set. And then the Hecke algebra acts on itself via right multiplication. And so to imitate this, we need to take our free module and give it an action of the Hecke algebra. And we can do this in two ways. We can either do it explicitly in terms of formulas, which I won't write down for you because they're not especially enlightening, but there are different types of orbits. And for each type, we can list how the Hecke algebra acts on those certain parameters. Or we can do a geometric construction and give an action in terms of push-pull functors. So we'll see a bit more of that later. Our next ingredient in Cauchy-Linguistic theory is Bruhat order. And so we need a partial order on our set. And again, I won't tell you exactly how it's constructed. It's similar to a closure order. Our elements are orbits plus local systems. So it's basically a closure order, but we have to keep track of the local system data as well. So it's a slightly more complicated partial order, but you can define one. And then the last thing we need is a Cauchy-Linguistic involution. And so here we can prove the existence of some involution in this module that satisfies appropriate properties. And then with all of this data, we get this theorem, which answers the question I just had a second ago, which says exactly how this multiplicity question is answered. So within this Lusztig-Vogan module, for every choice of parameter, we have two elements. We have the basis that is used to define the module, and then we prove the existence of some self-dual basis. And then if we write the self-dual basis in terms of the defining basis, the coefficients are polynomials, and if we evaluate these polynomials at 1, we get the multiplicities of irreducible admissible GK modules in standard ones. And these polynomials are called Cauchy Lusztig-Vogan polynomials. Okay, so the punchline of this whole first section is just that we've defined a set of polynomials at the change of basis matrix in some module, and their value of 1 tells us something about an important multiplicity question that has relevance for unitary representation. Great. Okay, so maybe I'll stop here. So this is all classical theory, but I'm not sure if everybody's learned it. So I went through it kind of fast. Are there any questions before I move on? Yeah.
I guess, so you're referring to the LV module, but it's the regular module for an algebra, right?
No, it doesn't have an algebra structure.
There's no algebra.
No, it's just a module of the Hecke algebra.
So which Hecke algebra is that?
Oh, the Hecke algebra associated to the complex group.
Okay.
So yeah, so we kind of forget about the whole real group, look at its complexification. There's a complex group, the associated Hecke algebra acts on these modules. Yeah, thanks for the question. Are there any others? So also I realize in normal life, I'm a very fast talker. Anyone who knows me knows this. But this seems to have been amplified by lack of sleep. So, and so please slow me down if I'm going way too fast. Okay, but so this was all, so I should say that all this story, so this theorem of Lusztig-Vogan is from 1983. So this story was all done in the 80s, and this multiplicity question was answered, and it was an important step in this world of real group representation theory, but it was a while ago. So it's not stuff that's been done especially recently. And also, this is a conference on categorification. And so now we're going to take this whole classical story and try to view it through a different lens, the lens of categorification. And that's where the work that I'm talking about comes in. So the idea is that we want to take this module over the Hecke algebra and view it as the shadow of something that's happening on the level of bimodules. So we want to find some Lusztig-Vogan category with an action of the Hecke category, so that if we take Grothendieck groups of everything in sight, we recover this classical story. And I probably don't need to spend too much time convincing you all that this is a good idea, but it is of note that this is almost what was done in the original papers. But the original papers were written in the 80s, and they didn't quite have this language, but they did define a category that they used to define this Lusztig-Vogan module to begin with. And so similar to the original construction was in some sense a categorification. But everything I'm talking about today is in a different language to the original papers. So they use a different geometry to what I'm going to talk about. And I'll just say 2 notes on why we might want to do this. The first is that this gives us access to other results about categorical action. And there are many of these days. And so if we can take this story of real group representation theory and frame it in this categorical language, then maybe we have more tools that we could use to understand things. And we can extract information about the module category by the category that's acting. And in this case, the Hecke category that's acting is a well-studied thing, and it has many incarnations, such as Soergel bimodules, and so we can use what's known about that category to tell us stuff about the Lusztig-Vogan category. So this is the idea, and the first step is to work geometrically, because the category is defined geometrically, or the modules defined geometrically. So the natural place for a categorification is in the world of geometry. And here I'll be quite brief, but feel free to ask me questions if you want more information about this perspective. So the geometry that I'll work in is the K-equivariant derived category of constructible sheaves of K vector spaces. So this is some big construction, but it's a nice triangulated category with 6 functor formalism. And it kind of behaves the way that you'd like it to. So it has IC sheaves in there that are parameterized by local systems and orbits. We can push and pull things as we like. And because we're looking at K-equivariant sheaves on Gmod B, there's a natural convolution action on the right of B-equivariant sheaves on Gmod B. So this K-equivariant derived category comes with a convolution action of the B-equivariant derived category. And then we can look within these categories to carve out smaller ones. So we can do 2 natural things. The first is within the K-equivariant derived category, we can take the semi-simple category, just generated by direct sums and grading shifts of IC sheaves. And in this case, like I said, IC sheaves are parameterized by K-equivariant local systems on orbit. So the IC have the same number of IC sheaves as we have parameters in our module. And then we can just take this category where we just take direct sums of them, and this is some additive category. And this has a natural action of the geometric Hecke category, which is defined to be the semi-simple category within the B equivariant derived category. So same construction, semi-simple IC sheaves, but now these are parameterized by elements of the file group. And the reason why this category is stable under this action comes down to the decomposition theorem. But it turns out it is stable. So if we take this, everything I'm doing here is working over a field of characteristic 0. So we can take the semi-simple category. It has a natural action of the geometric Hecke category. And we can also find another subcategory within it. So if we look within the semi-simple Lusztig-Vogan category, I can instead take all of the IC sheaves on closed orbits, and then I can act by the Hecke category. And this builds for me some subcategory of the semi-simple category. And I want to distinguish this one as well. So this I'll call the trivial block, and I'll explain more in a minute why I'm calling it that. But both of these two things are categories with an action of the geometric Hecke category. And then this construction, the point of this is a natural sort of categorical version of what I described on the level of modules over algebras earlier. And it turns out that if we take growth in D groups, we exactly recover what we'd like. So both of these categories I've defined here are additive categories. So we can take their split growth in D group, and the split growth in D groups are going to have an action of the growth in D group of the geometric Hecke category, which is the Hecke algebra. And we recover the Lusztig-Vogan module and a piece of it. So this bottom bit, this category generated by closed orbits, its growth in D group gives us what's called the trivial block of the Lusztig-Vogan module. So something that happens in this real group representation theory is that when we replace the Hecke algebra with this Lusztig-Vogan module, this has submodules. So it's not indecomposable. And these submodules play a really important role in the representation theory. And one submodule is maybe arguably the most important one, and that's the submodule that contains the parameter corresponding to the trivial representation. And that's what we get from this subcategory. So the smaller category gives us the block containing the trivial representation. Yeah.
A good technical question. So for the Hecke category, I know that you can sort of reconstruct all constructive proceedings using the homes of the category reconstruction theorem. Is there a similar reconstruction theorem on that side?
There should be, yeah. I think so. This is more of the language that these guys think in.
Okay.
But yeah, that can basically all these games that can be played with the geometric Hecke category, the same thing could be done in the K equivariant version. Yeah.
Block, do you mean a direct sum and?
Yeah. Yeah. So it decomposes into a direct sum of submodules, and there are a few of them. Yeah.
So that's indecomposable.
Yes. Yeah. Good point. This one is indecomposable. Yeah. Any other questions? Okay. So this was very fast geometry, and this is it's very interesting to think in terms of this world as well. And actually, this paper that I referred to on the first slide is mostly in this land. But what I want to talk about today is not this land. I want to talk about what happens algebraically. So I want to talk about an algebraic incarnation of everything I've done so far. So this is the second step, an algebraic categorification. And one nice thing about this geometric landscape, this machine of equivariant derived categories, is they come with a really natural bridge to an algebraic world. And that bridge is the hypercohomology functor. So if we take something in one of these complexes of sheaves in our equivariant derived category, we can take its hypercohomology, and this spits out for us a graded vector space. But if we have a complex of K equivariant sheaves, which is what we do, then what we get when we take the equivariant cohomology is we get a graded vector space that has an action of a graded ring, which is the K equivariant cohomology ring of the flag variety. So this functor takes some complicated geometric world and spits out a world where we can think about modules over a polynomial ring. And so that's what I want to do for the rest of this talk. And here is a place where I have to add a very important assumption. And this is the assumption that we need to assume now that our group is the identity component of this fixed point group. Because something that happens in real group representation theory is that these compact subgroups are often disconnected. And this makes things tricky in the theory because a lot of our theory works for connected groups. And so a lot of the work done in this world is showing that things still work in the disconnected setting. And unfortunately, this doesn't, or at least our arguments don't. So for all these algebraic arguments, we need to add a connectivity assumption, and this is the place where it goes in. Okay, so here's a quick lemma. I told you that if we take something in our category, apply this functor, I get a module over this ring, but what actually is this ring? And so if we take the k-equivariant cohomology of G mod B, this is a ring that looks like this. So it's the tensor product of two polynomial rings. The first is the symmetric algebra on the dual of the Lie algebra of the smaller Lie group. So that's what the TK is. So this is the torus of the compact group. And then we take the invariance under the Weil group of K of the smaller group. And then we take the tensor product of this with the symmetric algebra on the torus of the big group. And we can go one step further here. So our functor spits out a module over this ring, this tensor product, but then we can think about modules over this ring as bimodules, where the first thing acts on the left and the next one acts on the right. And so if we prefer, which I do, we can think about our hypercohomology functor as spitting out bimodules for two polynomial rings, one which captures information about K, and one which captures information just about G. Questions here? Okay. So a problem with this construction, this seems great so far. We have a functor that goes from our geometric world to a somewhat nice algebraic world, but the first problem with it is that this functor is not always fully faithful. If we restrict it to the semi-simple category. And essentially what it boils down to is the problem is that hypercohomology can't see these non-trivial local systems. And so what happens on these orbits is that we have interesting local systems. We already saw that in the SL2 example, and hypercohomology can't see them. Actually, and we can already see this in the SL2 example. So if we look at our open orbit, we have two local systems, trivial and Mobius band. And if we take the hypercohomology of the IC corresponding to the Mobius band, this is just the same as the k-equivariant sheaf cohomology, this local system, and this is 0. This local system has no global sections and no first cohomology, so our functor doesn't see this thing at all. So that's unfortunate. So what we have instead is we have a bit of a banding. This is why I introduced the other category. So if we restrict ourselves to this trivial block, the functor is fully faithful. And this was the main result of the paper with Scott. So the point is that in this algebraic world, we can't capture the entire Lusztig-Vogan module, but we can capture a big piece of it. And something that can be said is, arguably, this is kind of the most important piece. And we might be able to kind of restrict to looking at this piece in all cases. So we're trying to think about how this expands, but that's future work. What time did I start? I started at like
35 minutes.
Okay, so I should go to I have to 25. Okay, so what have I done so far? Let's see. So I built a functor. If I restrict it to this category, it's fully faithful. And so if we want to think algebraically instead of geometrically, we need to describe its essential image. So what's the essential image of this functor? Well, we can just mimic the construction that we had on the geometric side. So the generating objects should be what we get if we take the generating objects geometrically and take their hypercohomology. And so the generating objects were the IC sheaves on closed orbits, which are all trivial in this example, because we have a connectivity assumption. And so the hypercohomology is just the same as the k-equivariant cohomology of the orbit itself. And you can do this computation, and this is some module that looks as a ring like my polynomial ring P. Remember, P was the symmetric algebra of the smaller torus. But if we think about it as a bimodule, its right action of the ring is twisted by a certain element of the Weil group. So if you're used to thinking about Soergel bimodules and you're familiar with standard bimodules, these are the same thing. This is just a standard bimodule in a slightly different world. But the interesting thing that shows up is we have to ask ourselves which element of the Weil group do we get. And this boils down a little bit to the geometry of T fixed points on G mod B. So if we look at all of our torus fixed points, some of them are going to lie in closed orbits, and the cohomology of one of those closed orbits will be given by this standard module for the fixed points that are in that orbit. and all the fixed points in the same orbit yield isomorphic modules. So these are our generating objects. We don't have to describe them in terms of cohomology, we can describe them just in terms of the polynomial ring. And then from these, we just need to act by the Hecke category. And the algebraic version of the Hecke category is the category of Soergel bimodules. So I think that there are many talks in this conference about Soergel bimodules, so most of you probably know what they are, but here's a quick definition. If we take expressions of every element of the bio group, we can define R bimodules. This R is the same ring that's acting on the right in our category. And we can just take the tensor product over all the invariants under the simple reflections in this expression. And then we take a category generated by these things, closed under direct sums, summons, and grading shifts. And this is a monoidal category, and it categorifies the Hecke algebra. And it's exactly what we get if we take hypercohomology of the geometric Hecke category. And so then, what I want to define, my algebraic Lusztig-Vogan category, is what we get if we take these standard modules, act by Soergel bimodules, and and close again under direct sum, summons, and grading shifts. So this is our algebraic Lusztig-Vogan category. Any questions here? And so then, this is maybe a bit obvious at this point in time, but we now have an equivalence of categories. So we carved out exactly the biggest piece that we could find within the k-equivariant derived category where our functor is fully faithful, and then we describe its essential image, and so we have an equivalence. And let's do an example, just because now it's nice to see what this actually looks like. So what does this category look like for SL2? Well, I've showed you a little bit of its geometry so far. So in this case, what ingredients do we need for the category? We need the torus of the big group, the torus of the small group, and their associated polynomial rings and invariants. So in this case, things simplify nicely because our group itself, K, is already a torus. And so K is both the torus of the big group and the torus of the little group. And so that means that both of our rings in this L2 example are the same ring. And this is just a polynomial ring in one variable that's graded to be in degree 2. Okay, so for here, we're now thinking about a category of bimodules of the same ring. So things are looking a bit easier. And now we also need to think about Weil groups because there were some invariants that showed up in the construction. So the Weil group of K is just the identity in this case. The Weil group of the bigger group is Z2. And so that means if we take the invariants, again, we just get the same ring. So the upshot of this is that, yeah, the same ring acts on both sides. So now we have to figure out what the generating objects are, and I've defined them for you first as cohomologies of certain fixed points. So if we look at torus fixed points in our geometric picture here, they're the same as the closed orbits because our group K is torus. And if we take the T-equivariant cohomology of each of these points, well, as a vector space, it just looks like our polynomial ring. But if we keep track of it as a module, the action sees which torus fixed point we have. And so that means we have two generating objects, which are the standard modules corresponding to the identity in the simple reflection S. Okay, so these are two objects. Something that's of note, if you're used to thinking about Soergel bimodules, R is fine, that's a Soergel bimodule, but this standard bimodule is not a Soergel bimodule. So it's not actually in the category of Soergel bimodules, so already something very different is happening here. We get more of these standard modules within our category. And so then what does the construction say? We take these things and we act by Soergel bimodules. So if we act, this is just acting by a tensor product, and we can do a few computations to show us that if we take our identity, act by the indecomposable Soergel bimodule Bs, we just get it back. And again, if we take a standard module and act by Bs, we recover one more time, Bs. And if we take Bs and act on itself, then we get two copies of Bs up to grading shift. And so the point is that from this action, we see that the only thing we get by taking these two standard modules and acting by Soergel bimodules, the only new indecomposable we get is this Bot-Samuelson Bs. So from this computation, we can see that our category is generated by these three objects. It's two generators, plus it has Bs in there. And these are the three indecomposables in the category. So it's a relatively simple category, but already looks a bit different from Soergel bimodules. Any questions on this exam? Okay. So this means I have time to get to my actual examples, which is nice. Great. So this is what I wanted to get to for this conference, because so far I've told you a story that involves some classical unitary representation theory of real groups, and then a little bit of geometry. But I think the interesting question maybe for this audience is what these categories actually look like. So I've started with a real Lie group and built a whole collection of module categories over Soergel bimodules. And these categories tell us something about the representation theory of that real Lie group. But what do they look like? What kind of categories are they? So this is what I want to end the talk with. So how can we draw them? We want to draw module categories. What do we have so far? By construction, the indecomposable objects in our category should correspond to the IC sheaves in the trivial block of the geometric category. And the indecomposable objects in Soergel bimodules correspond to elements of the Bapat group. And we can take this category and split it into its cell decomposition. And so this is just a generalization of Lusztig cells in the categorical notion. We have a partial order on the indecomposables given by asking ourselves the question of when one shows up as a direct summand in the tensor product of another with some indecomposable in our acting category. And then this lets us split our category into cells. And it turns out that at least in type A, all the examples I'm going to show you today are in type A. These cells that we get are simple module categories over Soergel bimodules. And thanks to several people in the audience today, these things have been classified for finite Foxford groups. So what I want to do for the remainder of the talk is look at how we can take various ones of these Lusztig-Vogan categories and see what they look like, what their cell decompositions into simple Soergel bimodule categories are. So that's the remainder of today's talk. And it'll all be in type A for this, which already has some very interesting examples in the real theory. But of course, it would also be very interesting to see other types. So we'll start with our running example so far, SL2. So what does this look like? Well, on a few slides ago, I showed you that it has 3 indecomposables, which we figured out by direct computation, are 2 standard modules and BS. And there are 2 indecomposables in Soergel bimodules. And so we can draw the entire action of the category with a picture that looks like this. If we start with the W graph, which tells us information about the orbit closure relations and descent set data of our Lusztig-Vogan module, we can describe the action by kind of keeping track of how various things decompose when we act in this way. And so we've got arrows for each of our indecomposables. And from this, we can see the cell decomposition. So we can see from here that each of our 3 indecomposables lies within its own cell. So our cell decomposition of this SL2 example looks like this. We have our standard modules and the Box-Emerson. Now, what about Soergel bimodules? For type A1, this has 2 simple modules. And these are corresponding, each one, to the Lusztig cell, which we can label by Young diagrams. So we'll take these 2 Young diagrams with 2 blocks. And so then we can see that as a 2 representation of Soergel bimodules, this is our Jordan-Holder filtration of this SL2 Lusztig-Vogan module. This is basically just the same picture as that in a different order, parameterized by these guys. So this example is quite simple, but I wanted to show it so we get a sense of what these pictures mean, because now we'll draw them in examples that are a bit bigger.
W graph really capture the categorical?
In these type A examples, it does, but I think it won't in other types. Yeah. Which is nice because the W graph. So there's, if you worked in the world of real Lie groups at all, there's very nice software. It's Atlas and Lie group software, and this can spit out all this information for you and for big examples, which is useful. Okay, so let's see another example that's slightly bigger, still type A. So here's a more interesting real group, SU21. So first of all, what is this group? Well, I told you that I can define a group in terms of Lusztig-Vogan data. So here the data is a complex group, which is FL3C, an involution, which is that involution, conjugation by that matrix. And a finite subgroup of the, or a finite index subgroup of the fixed points. In this case, I'll take the entire fixed points, which look like a copy of GL2. So in this example, this is kind of a nice example because it's what we call equivariantly simply connected. There are no non-trivial local systems. And so there's actually just one IC for every orbit. So all we have to do is keep track of the orbit geometry in this example. And what this also means is that since we have no non-trivial local systems, our trivial block is the entire Lusztig-Vogan module. So here our algebraic category actually does capture everything. And then if we want to describe the orbit structure in this example, there's a very nice combinatorial gadget called a clan, which does this for us. I won't go into details about how it's defined, but it's a description of exactly these orbit closure relations for the groups SU, PQ. And in this case, there are six orbits. And if we look at Soergel bimodules of type 2, this has 3 simple module categories, again, given by Young diagrams. And so if we draw the same picture we drew before, these are our 6 orbits, and they're drawn in terms of their orbit closure relations. So the top one is a 3-dimensional open orbit. There are 2 2-dimensional orbits and 3 1-dimensional orbits. And the action looks like this. So we can see here, just by playing games and counting, that the Jordan-Holder filtration of this looks like the following. So we have 2 cells that have 2 indecomposables in them, and then we have the top cell and bottom cell that have exactly 1 indecomposable. So this is the filtration in this example. So this is about the extent, at least for me, of an example that I can really do by hand. So in this example, you can write down what the generating standard bimodules are, you can write down the action and play some games and figure out the decomposition. But higher than this, it gets a little bit out of control. And so for the rest of the examples, they were computed using Atlas. Any questions on this example? So this pattern generalizes nicely to SUN1. So what goes on here is our triangle kind of grows. And so if we look at the cell structure for these bigger SUNs, they look something like this. And now my picture's not as precise. We have more different colors of arrows acting, but we end up with 4 cells still. And we can see sort of by the clan data, which tells us about how to count the number of orbits, that there are this many indecomposables. And the number of cells for Soergel bimodules is given by the number of partitions of n-1 in this case, or n+1. Yeah, n+1. And so we have a certain number of simple module categories. We know how many indecomposables we have. And we also know the size of the simple modules, which is given by the number of fillings, the number of tableaux in some Young diagram. And so just with these 3 pieces of information, in this example, finding a Jordan-Holder filtration is just a combinatorial counting problem. There's only so many ways we can take these simple modules over Soergel bimodules, which are of a specific size, and get cells that are of this size that we have here. So our example has a really similar filtration to the one we saw in the smaller example. And something to notice about this is that if we look at the Young diagrams that show up here, these are exactly the ones which admit signed fillings with n pluses and 1 minus. And so by signed fillings, I mean alternating pluses and minus signs, where they have to alternate on the rows, and columns don't have to have any restrictions. And so this observation leads us to our final picture, which is that the same thing holds for SUPQ. So if we look at, SUPQ is a kind of interesting type A reality group, and its cell decomposition is exactly given by some signed Young diagrams. And this, it turns out, is a classical result of McGovern for the Hecke algebra from the 90s, I think, is when he did this. And so let's just see an example for SU2 because the combinatorics is kind of nice. So if we look at the signed Young diagrams with 2 pluses and 2 minuses that have 4 boxes, these are exactly all of them. Something to notice here is that we are allowed to permute rows which have the same number of boxes. And so that's why this one, if we switch these, it's the same diagram, so we don't get a different one there. And so we have this many signed Young diagrams. And then if we look at the decomposition of SU22, it exactly fits in like this. So these give us all of our cells, and this tells us its structure as a module category. over circle bimodules, which is kind of nice. So the upshot of these computations here is just that the story for type A has a very straightforward combinatorial answer, given in terms of signed Young diagrams. And the story for other types is to be determined. Yeah, question? So this is the end of what I have today. Thanks